Hello student, today we discuss the eigenvalue and eigenvector. Okay, basically you have seen, suppose you have a map from T R2 to R2. Okay, for example, suppose I am taking T of x1 comma x2 equal to, suppose I'm just taking some random map, x1 plus 2x2 3x1 plus 4x3, like that. So in first class I think we have seen this type of thing. You see, this type of map I can write as T of x1 comma x2 equal to you have a map 1 2 3 4 into x1 x2, right? Because this is some matrix product, but if you write in as a column vector, so you are getting the same thing, right? So this is your linear transformation, and if you write the linear transformation, the corresponding matrix form is your this 1 2 3 4. Okay, so what's happen if I give you some element? For example, if I say what is the value of T of 1 0, so you will get some element in your R2, like what how the function works, right? So if you put 1 0, what you will get? You will get, I think, 1 comma 3, right? This type of thing. If I say what is for T 0 1, so you will get I think 2 comma 4, like that. Okay, so for each image you can find the corresponding image. Okay, so basically this type of mapping is called linear transformation. Okay, so I'm just writing why this is called a linear map. Basically what's happened, just writing the definition of T from Rn to Rm is said to be linear if T of Cu plus dv, if you write this, you can write C into T of u plus d into T of v, where u and v belongs to Rm and CD belongs to your field R. Okay, so this type of thing you will learn more in detail whenever you will learn the vector spaces. Okay, I'm not going to that in detail. So if you see, if you apply this, you see this u and v is your Rn element. So if you're trying to check this operator I have written here, this operator are linear or not, so how you will check? So basically if you consider two elements, suppose T of, I am taking one element C into x1 comma x2 plus d into y1 comma y2. Okay, so if you break this thing, what you will get? Basically cx1 plus dy1 cx2 plus dy2, right? Now you apply on that one according to the transformation. So x1 plus 2x2, right? So cx1 plus dy1 plus 2cx2 plus 2 dy2, then 3cx1 plus 3 dy1 plus 4cx2 plus 4d sorry, am I writing any wrong? cx1 plus dy1. Basically you can think here, this is your new x1, right? This is your new x2, then you just apply your previous formula. So x1 plus 2 into x2, find 3x1 plus 4 into sorry, why I am writing x3, this is your x2. X2 is your cx2 plus 4d y2. Fine. Okay, so whatever you have, you just you have written this thing. Now you just do the RHS. So what you have to prove here? C into t of x1 comma x2 plus d into t of y1 comma y2. Why? Because your target is you have to show this one, right? So you just check, it will be definitely satisfied. Okay, x1 plus 2x2 comma 3x1 plus 4x2 d into y1 plus 2y2 comma 3y1 plus 4y2. Okay, so if you add this type of thing, x1 plus 2cx2 dy1 plus 2 dy2 3cx1 plus 4cx2 plus 3 dy2 plus 4 dy2. Okay, this type of thing. Okay, so you are getting same element, right? So that's it. So this is your linear map. Okay, now after that we'll discuss that eigenvalue and eigenvector. So basically, what is the definition of eigenvalue? I am writing eigenvalue. Why I have discussed this linear transformation, you will learn later, because this is related to your linear transformation. Okay, so first I am writing what is the definition of eigenvalue. Okay, so let A be a n cross n matrix. So for actually eigenvalue you can find always for square matrix. Okay, then a non-zero vector x, which is basically you can write n cross 1 type of thing. Okay, is called an eigenvector of A corresponding to the eigenvalue lambda if Ax equal to lambda into x. So here actually we have covered eigenvalue and eigenvector. Corresponding to lambda, this lambda is belongs to your f, or if it is real, so then it will be belongs to R. If A is a complex matrix, then corresponding lambda will belongs to just C. Okay, so it is like R or C. Okay, okay, depending on which field it is lying. So yeah, so basically whenever this type of thing is satisfied for your x and lambda, then I will say this x is my eigenvector and this is my eigenvalue, right? So this is AVS vectors AVL eigenvalue. Okay, now so how to find this type of thing? Okay, so basically you can have, if you write x minus lambda x, right? You have, so you see I can write this x minus this is equal to lambda I into x, right? Because any vector you can write into I into x, right? For example, if you have suppose 1 comma 2, this I can write is 1 0 0 1 into 1 2, right? So I can write this thing. Now after that I can have a minus lambda into x equal to 0, right? This type of thing. So this is equivalent to this relation also. Okay, now you see if your x is non-zero, for which you have this type of thing. Okay, so what is it saying? If you see earlier, if you consider new matrix, this type of thing. Okay, now basically you have a matrix, suppose this is your B, okay, and you have a x equal to 0. So you see x equal to 0 is always a solution, right? X equal to 0 is always solution, but you are not interested in 0 solution because you want a non-zero x, right? Basically you are one for which system which have more than one solution, right? And you know already you have seen in your there are 3 cases, right? If you see this type of thing, either it has consistent, so in consistent either it will be unique solution or infinite solution. There is not the case that there are 2 solution or 3 solution. That type of thing is not in your linear system. Okay, so obviously you want there is some infinitely many solution. So infinitely many solution, when you have, you see rank of AB equal to rank A, right? Rank of AB equal to rank A. If you have, you see here B does not have any role, right? Because right hand side you can have this is 0, so rank of you can say B, here you have 0, right? And rank of B equal to whatever it is, but it should be less than n. Less than n means it does not have the full rank. That means it's determined, you can say 0, right? Because already you have seen if it is n's, then your determinant will be in the non-zero, right? Because I discuss you with the minor point of view, right? That largest order minor, non-zero minor, that order is corresponding to a rank. Okay, so from there you can say that if you have, then you have determinant of A minus lambda I is 0. Okay, so this you can say. So how to find the eigenvalue? Basically from here, A minus lambda equal to 0. Okay, let's try one problem. Okay, example, let A equal to 2 1 1 2. Okay, so if you do A minus lambda I, because how to find the eigenvalue, you have to use this relation. Okay, so if you do determinant of A minus lambda I, so what you will get? Determinant of the matrix, basically lambda I, that means in the diagonal position you have to write minus lambda, right? With along with the A, so 1 2 minus lambda. Okay, so what is the determinant? 2 minus lambda in 2 minus lambda minus 1. So what you will get? 4 plus lambda square minus 4 lambda so lambda square minus 4 lambda plus 3, right? So if you solve this thing, lambda square minus 4 lambda plus 3 equal to 0, so from there you are getting actually the value of lambda is equal to 1 and 3, right? Okay, so in this way you can find the lambda. Now your job is to find the eigenvector. So you see there are 2 eigenvalue, right? Actually you will see whenever if your matrix is n cross n, so then it can have n order n eigenvalue, right? Why? Because you see in the diagonal position, always you have that minus lambda, right? So that will be multiply, okay, 1 by 1. Okay, and next. So how to find the eigenvector? So you will see for lambda is equal to 1 you will get one eigenvector, for lambda is equal to 3 you will get another eigenvector. Okay, so let lambda is equal to 1. Okay, so for this one you will get some eigenvector. Let the eigenvector is your x1 x2. So you have basically a minus lambda value is a minus lambda I into you have some x1, I'm writing some x1 x2, this is equal to 0, right? According to this one, right? A minus lambda I into x is your, because it will be 2 cross 2 vector, so I'm writing this, but here lambda is 1, so I'm this value 1. So what you are getting, basically 1 1 1 1, you see x1 x2, this is your 0 0. So from there you are getting x1 plus x2 equal to 0. So from there you have x1 is equal to minus x2. Okay, so you getting a relation. Yeah, you have two equations, both are you see same, right? Now if you have x1 and x2, so if you write in place of x1 equal to minus x2, so what you are getting, basically x2 if you take common, so minus 1 1, right? So eigenvector is your 1 minus 1 1. Yeah, instead of that if you write minus 2 comma 2, minus 3 comma 3, anything you can write, right? So this x2 is arbitrary, so eigenvector is your minus 1 1. This is the thing. Now for lambda is equal to 3, so you have a minus 3i into, yeah, here also you have some x1 x2. Yeah, you can use y1 y2, it is your choice. Okay, so minus 1, oh, both are minus 1, right? You see here your relation is not same, but still from here you are getting two equations, right? Minus x1 plus x2 equal to 0, for other is x1 minus x2 is 0, but both the equations are actually same, right? If you multiply it with minus 1, so from there you actually getting x1 equal to x2. So same if you do again, so x1 equal to x2 if you put, so x2 equal to 1 1, so this 1 1 is the eigenvector. Okay, okay, so what you have, eigenvalue 1, corresponding eigenvalue is your 1 minus 1, right? And whenever you're yeah, minus 1 1 1 minus 1, that anything you can write. Okay, because I told you, okay, I'm writing minus 1 1. Okay, and for 3 I have 1 1. Instead of 1 1 you can write, say 2 comma 2, no problem, even minus 1 comma minus 1. Okay, okay, so in this way you have to find the eigenvalue and eigenvector. Now what is the relation with your eigen that corresponding linear transformation? So if you consider the map earlier, so what is the corresponding map? This is the map, right? So you can have t of x1 comma x2, this is you have 2x1 plus x2 comma x1 plus 2x2, right? So you see, if you choose one point, so this is your domain set, suppose, and this is your range set. Okay, now suppose you are choosing some point from here. So for example, if you consider point 1 0 domain set, so what is this t10 going? t10 is going to, you can say 2 comma 1, right? 2 comma 1, so like that. Maybe here, right? This is the corresponding, it is going, right? If you consider any point, you will get the corresponding point in the range set. Okay, now what is happening for your this eigen value and eigenvector? So basically you just check here, if I consider my eigenvector, for example, if I choose that minus 1 comma 1, minus 1 comma 1 means at what direction? Or first we consider plus the 1 1. So 1 1 means what? 1 1 means, you can say this one, right? This 1 1 going to at what point? You see 2 plus 3, so this 1 1 point is going to your 3 comma 3, right? So you see it will be 3 comma 3. So the thing is, whenever you apply your operation on the eigenvector, that if you see this is the lying on that line, right? You can say x is equal to y line, this 1 1 point lies, the corresponding in the range set also still in the same line, 1 1 is going to 3 3, right? So whenever you apply on the eigenvector, that will lie in the same thing, that is the direction of that point will be not change. Okay, only there will be some stretching or compressing thing. For example, if you think what is the length of that, so this length may be, I think, root 2, right? This length. Now here this length is actually become 3 root 2. So 3 times of that you are getting. Length you can find root over x square plus y square formula, right? So in this way. So in case of your eigenvector, to apply, the direction will not change, it will multiply it with your eigenvector. Okay, so if you see for your what is happening for 1 comma minus 1 comma 1, so minus 1 comma 1, right? So this point, sorry, minus 1 comma 1. Okay, so if you apply this thing there, so what you will get, you see again you are getting, what is the point of t of minus 1 comma 1, you see, say again minus 1 comma 1, right? So you see same. Why? Because here eigen value itself 1, so there is no change, right? Yeah, if you think if you are getting some negative eigenvalue, the direction is changed, but it is not true because it is multiplied with minus 1, right? So but still it is on the same direction, same line. Okay, so in this way you have there is a relation between linear transformation and your eigenvalue and eigenvector. You can visualize with your geometry. Okay, so this is your eigenvalue and eigenvector. Okay, now I am giving you some homework. Find eigenvalue and eigenvector for 1 3 4 2. Okay, this is I'm giving this. Okay, now I am trying one more difficult, that is suppose 3 cross 3 matrix. Just I will practice one of them. let's try this one. I just give you hint, okay? You have to do the total thing problem. So same problem, find the eigenvalue and eigenvector of, suppose I am considering this matrix 4 0 1 2 3 2 1 0 4, this type of matrix suppose I am considering. So in this matrix you have to find the eigenvalue. So how to find? Suppose this is your A, so what you have to do, determinant of A minus lambda I equal to 0. Basically you have to find the corresponding thing, right? 4 minus lambda 0 1 2 3 minus lambda 2 1 0 4 minus lambda. You break the determinant, okay? From there you find the corresponding lambda value, okay? You will get some lambda q type of equation. This is your task. From there you will find the lambda will be 5 3 3. It has actually two eigenvalues same, okay? Anyway, now I am trying to find the eigenvector, okay? So suppose lambda is equal to 5, okay? So how to find? So A minus 5i into, you have here you have 3, right? This type of thing, okay? So if you apply this thing, so basically minus 1 0 1 2 3 minus 5, that means minus 2 2 1 0 4 minus 5, that is minus 1 into x1 x2 x3 into, right? So from there basically whenever you are trying to find this, you have to use two relation from here, okay? So minus x1 plus x3 equal to 0, one of the equation, and next you have 2x1 minus 2x2 plus 2x3, this is equal to 0, right? This two thing you are getting. So one of the relation you have x1 equal to x3, and if you apply this thing here, so from there you just find what are the value of x2. So you just check, mm, 2x2 will be 2x1 plus 2x3. So I am writing everything in terms of x3, okay? So you are getting actually 2x2 equal to 4x3, that means x2 is equal to 2x3, right? So if you apply your the previous thing, right, x1 x2 x3, right? You see I have not used the last relation because this is same as your first one if you multiply with minus 1, okay? So x3 2x3 x3, so what you are getting from here, x3 common 1 to 1, okay? So eigenvector is your 1 to 1, okay? Fine. So this is we have find for lambda is equal to 5. Now what we will do for lambda equal to 2? Same thing, okay? You just try for lambda is equal to 2. I am writing what are the equation you will get directly. x1 you do the job, okay? Next you will get x1 plus x3 equal to 0, 2x1 plus 2x3 equal to 0. These two equation you will get. Okay, you see both of the equation is actually the same thing. It is given. You have another equation x1 plus x3, but all the equation are same, right? You have actually x1 is equal to minus x3, but x2 is your free variable, okay? So what we will do here, you have x1 x2 x3, right? So if you put x1 is equal to minus x3, so minus x3 x2 x3, okay? So from there actually you can write x2 common 0 1 0 plus x3 common minus 1 0 1, right? So these are the two eigenvector. Okay, so eigenvector are, because you have two eigenvalue, right? This two will sorry, this is 3 actually. This 3 is occurring 2 times, right? So that's why you have 2 eigenvector. Fine. Okay, this is done. Next, your task is one of the 3. Okay, let me find some problem. You just try this one. This type of problem is coming. Okay, so practice this problem. Suppose you have 3 1 1 2 4 2 minus 1 and 1. Okay, if this 3 order matrix comes, obviously it will 6 marks. Okay, next I'm write the next theorem, that is called the Cayley Hamilton theorem. Okay, before that I'm writing what is characteristic polynomial. What is this? Suppose you have a matrix A. Okay, so for this one you have the equation det of A minus lambda, right? That equation is actually called the characteristic, nothing else. Polynomial of A is a determinant of A minus lambda I equal to 0. So whenever you are doing, you will get some lambda to the power n equation, right? That is the you will get some polynomial of order of degree n, right? So that type of thing is actually you can write lambda to the power n into plus cn minus 1 lambda to the power n minus 1 plus cn minus 2 lambda to the power n minus 2 plus dot 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 c1 lambda plus c0 equal to 0. So this is depending that cn minus 1, cn minus 2, c1, c0, this type of value you can find from the determinant depending on the matrix. For example, whenever we have find this equation for the first one, you see where I have find, yeah, this one, this is equal to 0, right? So you see this is your lambda square plus here actually my c1 is minus 4 and c0 is your 3, right? This type of thing. Okay, now this type of polynomial is called actually characteristic polynomial. Okay, now what is the Cayley Hamilton theorem? Okay, before that I am trying one more problem. It is coming in your previous I think I have seen in your previous paper. Very important problem. Every matrix has a real eigenvalue. Okay, still now we have not done any all the eigenvalue is real, but you may got complex also. Okay, so basically if your matrix is symmetric, then it must have real eigenvalue. I think we have not done any real one also. Yeah, this is actually symmetric, right? So then you can ensure that your eigenvalue is always real. Okay, so this thing is your statement, so this you have to prove. Okay, so how to prove? So basically let lambda be the lambda, okay, if possible let lambda belongs to C, that means complex number. So you have x equal to lambda x, right? So if you take the conjugate both, you know conjugate, I think Somi sir is discussing this. So basically you have a conjugate x conjugate equal to lambda conjugate x conjugate. Okay, now you know whenever you have this a bar a conjugate, but a is real matrix, so this thing you can write as ax bar. Okay, now suppose you are multiplying with your x conjugate transpose both side. So what you will get, you see this is some real number, so you can change the position. Okay, so this type of thing you are getting, right? Now you see I can write this thing is x bar transpose into a transpose. Now you see, you know why I am writing, because you know a to the power transpose equal to a, right? Now this thing you can write a x bar whole transpose into x bar equal to lambda bar x bar transpose into x, right? Now what is your a x bar? A x bar is your actually lambda bar x bar. I think there is some mistake. Okay, what you have, so suppose you have find this thing. Okay, so a x bar equal to lambda x bar, this you have, right? Now you have to group two things. Okay, so basically suppose you have x bar transpose ax, so what you can write, this is you can write x bar transpose into ax, that means your lambda x, right? So from there you have lambda into x bar transpose into x. Okay, now you have suppose ax bar into x. Because you see this is also same, right? Because if you have ax bar its transpose, if you apply this x bar transpose into a transpose, right? A transpose is this thing, right? Anyway, so if you think from there that, okay, again x bar transpose a into x, this is equal to, you can write this, so this you can write x bar equal to what, lambda bar into x bar, right? This transpose into x, so lambda bar x bar transpose x. So you see both thing is same, right? So you have lambda into x bar transpose x into lambda bar into x bar transpose x, this type of thing. So what you are getting from here, lambda minus lambda bar into x equal to 0. So from there you have actually lambda equal to lambda bar, that means, so for which type of element you have the, so here basically for which type of element you have its conjugate equal to that one, right? So basically lambda equal to lambda bar for which type of thing? Whenever your element is real, so eigenvalue is real. You remember this thing is actually always non-zero. Okay, you can try for any non-zero x if you take, and you take its conjugate and transpose, so overall you will get some always positive thing. Okay, you just check. Anyway, this is called actually the squared norm. Okay, you can if your x is like x1 x2 type of thing, then you will get that x bar transpose x, you will get this is your summation, that is x1 square, sorry, modulus x1 square plus modulus x2 square. You just try this one. Okay, so this is always positive thing, so obviously this would be 0, so this gives you this result. Okay, next I am explaining discuss the Cayley Hamilton. Okay, so this is saying that every square matrix satisfies its own characterization. In its own characteristic equation. Okay, so what do you mean by that? Suppose for a polynomial you have find. Okay, so for example, I am taking the first example. It is just for 2 order. Yeah, a is equal to 2 1 1 2. For this one you have the eigenvalue sorry, yeah, 2 1 1 2, right? For this one you have find the characterization is this. Now what Cayley Hamilton theorem says, that matrix itself satisfy this one. So basically if you find a square minus 4a plus 3, obviously in whenever you are writing matrix, so you have to write 3i. If you find this thing, you will get 0 matrix because it is in equation form. Correspondingly you have to think the corresponding matrix equation. Now just try, what is your a square? A square you just find 2 1 1 2, so into 2 1 1 2. So basically what you have, 4 plus 5, 4 plus 2 6, 2 plus 2 4, 1 plus 1. Okay, so now do a square minus 4a plus 3i. So here you have 5 6 4 5. After that you have minus 4 into a, so basically 8 4 4 8 plus 3 0 0 3. Okay, so from there you are getting 0 0. Maybe I am finding this 6 element wrong, because always you have to get the same answer, should be 0. Okay, so 5 is fine, this is also fine, but here you are not getting 0. Why? 6, so this should be 4. Yeah, this is 4, sorry. to 0 0 0 0. Okay, so you see you are getting this. So Cayley Hamilton theorem says this. Okay, so there is some application. Okay, for example, suppose a question asks, find the inverse of 2 1 1 2 using Cayley Hamilton. Okay, so how to find, because so basically what you have obtained, a square minus 4 into a plus 3 into I is your 0, right? So from there you have a square minus 4 is equal to 3 into I. So if you take common a minus 4i, this is your 3i, right? So you can have a into 1 by 3 into a minus 4i, this is equal to I. You know what is your matrix inverse? Basically if you multiply a with that matrix, you will get identity matrix. So from here you can have the a inverse is 1 by 3 into a minus 4i, right? Okay, so this type of thing. Now you just substitute the value of a and I, then you can easily find the value of a inverse, right? So this is else. Now suppose there is another thing. Suppose they ask find AQ, higher power. Okay, so you see already you have find a square is equal to 4a minus 3i, right? So if you multiply with AQ, so what you have, 4a square minus 3a. So what is your 4a square? 4a square, again you just substitute what is the value of a square. A square is your again 4a minus 3i minus 3a, right? So from there you have the value 4 4 16a minus 3a, that is 13a minus 12i, right? So you see I am not multiplying the matrix multiplication, but I have the answer. This is easy to find, right? You just multiply, substitute the value of a and you get the answer. So these are the application of your Cayley Hamilton. Okay, so this complete this thing. In next class we discuss the some previous year question and go to your classical algebra. Okay, bye. You just try this homework. Okay, bye.